Welcome, everyone. For today's prep, we're going to start looking at how to represent certain functions using a power series. So specifically, we're going to start looking at how to represent functions that can be generated from this special function 1 over 1 minus x. And we'll see why this function is special in a few seconds here. All right, so let's start by just kind of going back to geometric series. So we're really getting our money's worth out of this geometric series. So we know that the general formula for a geometric series is the sum from n equals 0 to infinity of some constant a times some constant r raised to the power n. And sometimes it helps just to kind of picture these things by writing out the first few terms. So a plus a times r plus a times r squared and so on. And we know everything there is to know. Well, we know a lot about geometric series. So we know that the absolute value of r being less than 1 makes this geometric series convergent. And in this case, we can actually figure out the sum. So we've got our geometric series in terms of a and r. And, well, we have a nice little formula for the sum of that series precisely when the absolute value of r is less than 1. So we know that the sum has this formula a over 1 minus r. Okay, now we're going to use this formula and we're going to convert it to a power series. And the way we're going to convert this to a power series is we're going to set a equal to 1 and we're going to set the r value equal to variable x. This is going to give us a power series then, and it's going to be the series, the sum from n equals 0 to infinity of x raised to the power n. And if we, again, write out the first few terms just to see what this thing looks like, it's 1 plus x squared plus x cubed, and so on. So here we got a power series, powers of x. And the convergence is still the same though. We need the absolute value of that r value, in this case x, to be less than 1. And in that case, when that happens, we can figure out the sum of this series. The a value we said was 1, so that was the a value there. We're just setting it equal to 1. And normally it's 1 minus r, but in this case we're setting r equal to x, so it's going to be 1 over 1 minus x. All right, so this function 1 over 1 minus x, this is special. And what we're going to do is we're going to view this equation kind of two ways. So this is where we're getting to the representation. So what we just did is we're viewing 1 over 1 minus x as the sum of this power series. So we're viewing this as a sum, and this is the power series. Okay. Well, what we're going to do is we're going to flip that around. We're going to flip this equation around. And this is going to give us a way to think about representing certain functions using power series. So instead, what we did before is we said, here's a power series, and we know based on the r value, we can figure out the sum of that power series. Well, we're flipping it around. So now we're going to view this as just a regular function, 1 over 1 minus x. And we can make this equal to, we know it's equal to, a power series. So over here, we have a function. And we're going to have this function, and we're going to figure out the power series, a power series that's equal to it. So this is going to be our power series representation. Okay. So, and we're going to do this with other functions, not just this 1 over 1 minus x. but this one's going to be our special one that we're going to use. It's going to be our prototype. So let's just kind of state everything there is to know. We're going to be coming back to this one. So we're going to, just for simplicity's sake, I'm going to call this our prototype. So we're going to be, looking at all sorts of functions that kind of resemble this thing. And our task is going to be to find a power series representation. And we're always going to be coming back to this prototype. So, exactly what we've seen before. And we just have the extra note here that for a geometric series, we know the interval of convergence. So for this thing, it's the absolute value of x is less than 1. So that gives us the interval of convergence, everything between -1 and +1. And a geometric series diverges at the endpoints. So, we could check the endpoints and see that they're divergent. And the radius of convergence here is 1. All right. So when we look at this prototype, there's kind of a few important little things that we need when we go forward. So we're going to be looking at compositions and functions that get multiplied. And in order for us to represent a function, there's two things we're going to need. So the first thing is we're going to need a 1 right here. And then the second thing is we're going to need a minus sign. We're going to need subtraction in the denominator. So those are kind of the two important little pieces that we're going to need. So we need this subtraction sign, and we need that 1 in our denominator. All right, so right now, kind of being a little ambiguous about this. So let's look at an example, and we'll see what we mean. So let's look at example 1. And we have this function 1 over 1 plus x cubed. And let's find a power series representation for this function. So the idea here is this function sort of looks like our prototype, 1 over 1 minus x. So the idea is we're going to just kind of rewrite it so that it's a little more closely in that form. And what we mean by that is we need a 1 right here, which we already got, but then we need a minus here. So step 1 here is to rewrite it in our prototype form. So our prototype is 1 over 1 minus x. So in our case here, we need that minus. So we have 1 over 1 plus x cubed. And the 1 was good. That one's good. But we got to do something about that plus sign. We need to make that into subtraction. So we're just going to make that into a double negative. So we end up with 1 over 1 minus negative x cubed. And at this point, we're kind of ready to go. So we can identify the r value. That's the next step. So we identify the r value. So the r value in this case is negative x cubed. All right. So now we're going to plug this into our formula for the prototype. So good practice. Let's just write out the formula for our prototype. and I'm probably going to overuse that word. So 1 over 1 minus x is 1 plus x squared plus x cubed plus so on. And if we write it out in sigma notation, it's the sum from n equals 0 to infinity of x raised to the power n. All right, so that's our prototype formula. And what we're going to do is we're going to take this r value and we're going to plug it in to this formula. Normally where r would be. Or in this case, we're going to plug it in wherever we see an x. So all these x's that we got, we're just going to replace with negative x cubed. So we're going to have 1 plus negative x cubed plus negative x cubed squared plus negative x cubed cubed, and so on. And then if we plug it in also to our sigma notation here, we'll have, instead of that x, it'll be negative x cubed raised to the power n. And we just want to simplify this down a little bit. So in this case, nothing to simplify here, but if we kind of square this out, the negative is going to get canceled, so it's just going to be addition. And when we have multiple exponents like this, we multiply them together. So we're going to have x raised to the power 6. And then for when we have odd powers, the negative is going to survive, so we're going to have minus here. And then we multiply the powers of x, or we multiply these exponents, so we get x raised to the power 9, and so on. And if we do the same thing for our sigma notation, again, we're going from n equals 0 to infinity, the only thing we want to do is we kind of want to break off the negative and the x cubed part. So to simplify this down a little bit, we can rewrite this negative x cubed raised to the n. We can kind of distribute that exponent. So we can distribute the exponent to the negative 1. So we get negative 1 to the n. And then we can distribute the exponent to the x cubed part. And just like we did in all these previous ones, we multiply the exponents. So we end up with negative 1 raised to the n times x raised to the 3n. So now we have our nice power series representation. So we have negative 1 raised to the n, and then x raised to the 3n. And so this gives us our representation. So now we have a way to think about this function 1 plus x cubed. This on its own, this is a perfectly good function, good looking function there. But now we have a way to think of this also as a power series. So an alternative version of this formula would be the sum from n equals 0 to infinity of negative 1 raised to the n times x raised to the 3n. So this is going to be helpful, this idea. We're going to be able to turn functions like this that have a nice little closed form formula like this, just power of x, and we're doing a little bit of division there, into a power series where we're just adding up powers of x. So this is going to be helpful, especially when we get to some calculus with these things. But for right now, we're going to try out a few more of these examples in class. So we'll see you then. Bye-bye.